Hey everybody! So today we're going to talk about sets. Sets are really fundamental in mathematics. In modern mathematics, just about everything is based on sets. And so we're going to learn a lot of methods in this lecture about how to prove things involving sets. In particular, we're going to learn how to prove when sets are equal or how to prove when one set is a subset of another set. Even in this class, everything that we do after talking about sets is based on sets. Relations, functions, binary operations, they're all just special kinds of sets. And so whatever we learn to do about sets, it applies to all that stuff. So really important stuff that we're going to talk about today. All right, so let's jump right in without further ado. Now, some of the first things that we'll talk about, we've kind of already been talking about it, and you've probably seen it in previous classes. But as we move along, we'll get into some new material. I'm sure it'll be new to you. But it's good to start with some things that are a little familiar. So let's start with the idea of sets. So what is a set? Well, a set is one of those things that it's so basic that it's even hard to give a good definition of it. You end up engaging in sort of circular reasoning. It's really rock bottom. The only thing you can really do to define a set is to use synonyms of the word set. So we define a set to be a collection. You might say, well, what's a collection? But it's an undefined word in terms of math. But basically, the idea is a set is a collection of objects, and the objects that are in the set are called elements. And as a matter of convention, we tend to use uppercase letters to denote sets, but that's not always 100% the case, but most of the time it's true. And we tend to use lowercase letters to represent the elements of sets. And whenever you have an element X in a set S, we use this notation. And that symbol there is a Greek epsilon. And it's E for element, right? So we've been using that notation already quite often. And of course, if we want to indicate that Y is not an element of S, we'll use the element symbol with a slash through it. So basically, Y not an element of S means the same thing as not Y is an element of S, like that. It's just the negation of the statement, Y is an element of S. So if we look at this set here, A is 1, 2, 3. The element 2 is an element of the set A, while 4 is not an element of A. Okay? Now we have a few different ways that we can describe sets. Each of these methods has its place, and they're all correct. One of them is more powerful than the others because of it's more generally applicable to describing sets. But the first way is simply list the elements in the set. And we use brackets to indicate the set. So we've already done this up here with A. That's an example of that. It's not hard to give you another example. How about B equals little a, little b, little c? So we always use those curly brackets to indicate that we're talking about a set. We don't use parentheses or any other sort of grouping symbol to indicate a set. If we use parentheses, it actually has a completely different meaning. Typically, people use parentheses to talk about sequences, which is a different kind of mathematical construction. And then 2, we use something called set builder notation. And I'm going to talk about that more fully on the next page. I bet you've probably seen set builder notation at some point in the past, but we'll definitely review it. And the third thing is to indicate a pattern. This is a nice way if you have a set that is really just sort of a continued pattern, and it may be hard to describe with a mathematical formula, but nevertheless the pattern is more or less clear. There's not much to talk about with the first thing. You list the elements. You list the elements, right? You just write them down. Now, of course, it's clear that the disadvantage of listing the elements is if you have a very large set, it can be very difficult to list all the elements, right? So it's listing the elements is a very limited method. But set builder notation is very general. You can describe any set using set builder notation, and indicating a pattern has some area of applicability whenever there's a clear pattern. So let's talk about set builder notation briefly. So here's the scheme for set builder notation. I've got it indicated here. You still use curly brackets to indicate that you've got a set. And then what you do is on the left-hand side, you specify a variable that represents an element. You specify a set that element has to lie in. This is called the universal set, or sometimes we call it the set of discourse. It just says, what kinds of elements we're talking about. And then you specify a property that X must satisfy to be a member of the set. That's called the membership condition. This bar in the middle here just reads such that. So overall, this notation reads the set of elements X in the universe U such that, or with the property that, P of X is true. The condition P of X has to be true for a particular X in order for that particular X to be a member of the set. So for example, if I wanted to describe the set of even integers, I could describe it. There's more than one way to do this, but here's one way. I could describe it as the set of integers n, so the set of n and z, having the property. We can also use a colon instead of a vertical bar, with the property that there exists a k in the integers such that n is equal to 2 times k. This over here is a membership condition P of n that says if a particular n satisfies this condition, then it's a member of the set. Now, if you have a particular n and there exists a k such that your n is equal to twice k, that's the very definition of what it means for n to be even. So this describes the set of even integers on the nose. In the second example here, I'm giving you set builder notation, and I'm asking you to kind of tell me what is this set. So this is the set of integers, x and z, with the vertical bar there, such that the absolute value of x is less than 3. Okay, well, if I think about that, there's lots of integers, but there's only a few that are small enough that their absolute value is less than 3. In particular, those integers would be -2, -1, 0, 1, and 2. 3 and -3 are not included because it was a strict inequality. Now, one thing that's important when you're using set builder notation is the universal set is super important. If you don't specify a universal set, then there can be a lot of confusion. In this example here, I've not specified a universal set. Now, it's not necessarily wrong to omit the universal set. Sometimes, if the context is clear and there's no possible chance that someone's going to be confused, you might drop the specification of the universal set because, it's just redundant because of everybody knows what the universal set is. For example, when you're in a calculus class, the universal set is almost always the real numbers. And so if you drop saying that the x's were in the real numbers, well, you could probably be forgiven. But when in doubt, be sure to include a universal set. So, for example, if you would compare the set of x in the integers, where absolute value of x is less than 3, and you would look at the set of x's in the reals, such that the absolute value of x is less than 3, you get two completely different sets. The first one we did that previously, that was -2, -1, 0, 1, 2. But if x is in the reals instead of just the integers, what you end up with is you get this open interval on the real number line from -2 to 2. I'm sorry, -3 to 3. And so you get all those infinitely many numbers in between -3 and +3 because you get all the fractional values and all the weird values like square root of 2 and e and weird stuff like that, right? Whereas in the previous set, it's a finite set. It only has 5 elements in it. So it's clear that these two sets are completely different sets, even though their description, like they have the same membership condition, but the domain of discourse or the universal set are different, so you get a different set. So that's something you want to be super paying attention to, okay? The third way that I indicated that you can describe a set is to use what are called ellipses. And we're not talking about the sort of oval-shaped curve. An ellipsis is like the ... thing that you use to indicate that a pattern continues. So for example, the set here, the set of natural numbers having the property that 5 divides that natural number. Well, if you think about it, that's just the set of multiples of 5. So this would be, okay, 5 and 10 and 15 and 20. And at some point you go, yeah. Okay, well that's when we put that ... to indicate the pattern continues. And if the pattern continues, clearly it's not a problem. You can totally use that notation. You just want to be careful. If the pattern isn't clear, or if the pattern is super complicated and it's going to, it's like one of these genius tests to figure out what the pattern is, then probably that's not the right notation that you want to use. In the second example I have here, maybe that pattern's clear enough. Like, to me, I'm thinking, well, they probably mean a set of prime numbers. But maybe I'm just misreading it. Maybe it's something else. Maybe it's, I don't know, maybe if I try to put on my genius pattern detection hat, maybe it's something like, okay, the gap here is 1, and the gap here is 2, and the gap here is 2 again, then the gap is 4. So maybe it's going to be something like the gap is 4 here, then 4 here, then 4 here. And then the next time it's going to be, maybe it's powers of 2. Like, so it's 8, 8, 8, 8, 8, 8, 8, 8. Maybe it's doing something like that, right? So maybe the pattern is doing something like, okay, 2, 3, 5, 7, 11, 15, 19, 23. So there's 1, 2, 3, 4, So anyway, I think the moral of the story is clear here. If the pattern isn't 100% clear and without any chance of being messed up, then you should probably just use this notation. So this notation that I used here is perfectly clear about what elements I'm talking about. This one over here is still a little foggy. Who knows what that is? So that's the advice. Unless the pattern is perfectly clear, use set builder notation. There are times though where the pattern is easy enough to sort of describe it, then like it's easy enough to see when you put the ... someone will go, oh yeah, I see what's going on, but it can be then difficult to come up with the right notation to describe it in terms of set builder notation. But usually if you think about it, you can come up with good set builder notation to describe the set. All right, so let's do a little skills check here on set notation. So I've got a couple problems here, and I just want you to take a few minutes, press pause on the video like usual, and do these problems, and then when you come back, we'll do them together. All right, welcome back. So true or false, is 12 in this set of integers n with the property that 3 divides n? So first of all, you ask yourself two things. Is 12 in the universe in question? Yes. And then secondly, does 12 satisfy the membership condition? Does 3 divide 12? Yes. So then it's in the set. So this is true since 12 is an integer and satisfies 3 divides 12. Part B. Is square root of 2 among the set of real numbers whose absolute value is less than 2? Yes, this is true. We know square root of 2 is a real number, and we know that the absolute value of square root of 2, square root of 2 is roughly 1.414. So that's less than 2 when you take the absolute value of it. How about the part C? Well, part C is false because square root of 2 is not in the correct universe there. We're looking at integers. X is an integer. It does satisfy the membership condition, okay, just like it did in part B, but it's just from the wrong universe, so false, since square root of 2 is not an integer. Okay, part number 2. Use set builder notation to describe the set of natural numbers that are divisible by 10. Okay. It says you can read from the context of the question. It says the set of natural numbers. Okay, so that's our universe. So I'm going to say the set of n and the natural numbers having the property, and then the property that is our membership condition is that are divisible by 10. So I need those n's to be divisible by 10, so I'll say with the property that 10 divides n. Whenever I have to use a vertical bar in the membership conditions in the problem, this is a good time to, instead of using a vertical bar to mean such that, you can use a colon instead. And if I need to use a colon in the membership conditions, maybe I'll use the vertical bar instead. Just a little advice on making the notation, read clear. What? I'm not wearing a new t-shirt. You're wearing a new t-shirt. All right, so next let's talk about set containment. So we say A is a subset of B, and we use this notation. You've probably seen it before, the subset symbol there. It just means that if you have an X that's in A, then that X also has to be in B. So an element in A has to be an element of B if A is a subset of B. We also use this language that A is contained in B if A is a subset of B, or we say B contains A. And then lastly, whenever we have A is a subset of B, but we also know A is not equal to B, then we use this notation and say that A is a proper subset of B. So, we're trying to mimic what the difference is between less than, like strictly less than, or less than or equal. So over here on the right, you have less than or equal, and then you have strictly less than. It's sort of analogous to subset or proper subset, because these top notations here allow for the possibility of equality, but the bottom ones do not allow for the possibility of equality. Let's look at a quick example here, just sort of a toy example. So one thing that is important when you're talking about sets is that you typically have to have in mind some sort of universal set. So a universal set is just the set in which everything is taking place. So if you want to restrict to the integers, you can do that, or you can have the real numbers be your universal set. The universal set can be whatever you want it to be, but you have to have something in mind like that. So in this example, our universal set will be the integers. And then we have the set here, A is just the integers 1 through 10. And B is the set of integers -10 up to +10. And then C is just the integers 0, 1, 2, and 3. All right, so one thing I see here, I just want to kind of go over some relationships I see among the sets listed here. Like for example, we can see that A is a subset of B because every element that's in A is also in B. And also A is not equal to B, so I can also see that A is a proper subset of B. So both of these things are true. These aren't mutually exclusive ideas. It's true that A is a subset of B, but it's also true that A is a proper subset of B. Just like it's okay to say 1 is less than 2, and it's also true to say 1 is less than or equal to 2. Both of those things are true. I also see that C is a subset of B, but C is not a subset of A because C has one element that A does not, 0. Okay, and I want to talk a little bit about the logic of when you say A is a subset of B. When you look at the definition, it's not completely transparent, but this part right here, if for every X in A we also have X in B, one way that we can phrase that is to write it this way. We can say if A is a subset of B, then it means that for every element X in the universe, whatever the universal set is, the universal set simply has to be some set that contains both A and B. But anyway, it means for every element of the universe, if X is an element of A, then X is an element of B. So this logic right here is super important because we'll be needing to use this logic whenever we're doing proofs involving set containment. So it's a conditional statement here, right? That's universally quantified. So we know how to prove these things. We worked on proving universally quantified statements in the past. So, basically proving containment comes down to picking an arbitrary element of A and then arguing that that same element is in B. But we'll come back to that in just a moment. Before that, I want to talk about another concept, the concept of the empty set. The concept of the empty set can be a little bit of a, I don't want this to be a huge philosophical discussion, but the empty set is simply this set that we'll denote by a circle with a slash through it, and it's just a set that doesn't contain any elements. So it's sort of an empty set. We also call it the null set or the void set. You can kind of think of the empty sets kind of like 0. Numbers describe quantities, right, or magnitudes. And the number 0, for a long time, we didn't even have the concept of the number 0. because why would you have a number to represent nothing of something? But of course, it turned out to, that in fact it's really important to be able to express nothing of something, an amount of nothing. And similarly, it's very convenient to have a set that is sort of the nothing set. And one important property of the empty set is expressed here in fact 2.8. And the property is that the empty set is a subset of any set. You give me any set, the empty set is a subset of it. Let me prove that for you, because it's some interesting logic. It'll tie back into what we had in the box up here a second ago at the top of the page right now. But it's also going to tie into some logic that we previously discussed. So let's talk about it. To prove fact 2.8, we need to start off by letting A just be some arbitrary set. And let's specify a universe that contains A. To prove that the empty set is a subset of A, we must show that, the logic that we talked about in this box up here holds, that for every element in the universe, if X is in the empty set this time, then X would have to be in A. We must show that for every X in U, if X is an element of the empty set, then X is an element of A. Well, to that end, let X be an element of the universe. Well, I just want to point out something about the logic here of what we have to prove. For the conditional statement, X element of empty set implies X is an element of A, the hypothesis is false, since the empty set has no elements. By definition, right? The hypothesis X is an element of the empty set is just false because X can't be in the empty set has no elements. So whenever you have a conditional statement whose hypothesis is false, the conditional statement on the whole is true. So the conditional statement that we wanted to prove, X being in the empty set implies X is in A, is true, just because the hypothesis of that conditional statement is false. So we're done. Thus, empty set is a subset of A. So I think we mentioned this terminology back in the logic section, but anytime that you have a conditional statement like this with a false hypothesis, we call this a vacuously true conditional statement. It's impossible for the hypothesis to be satisfied in that conditional statement, so we say it's vacuously true. So all right, so saying that the empty set is a subset of any set is sort of a vacuously true statement, but true nonetheless. The next concept I want to talk about is the idea of set equality. So you might be thinking, why do we need to talk about what equals means? Equals means equals. Well, probably we're all guilty of not really giving that much thought to what equals actually means. Like, what does it mean to say two numbers are equal? Do we have a firm definition of that somewhere? Like, for example, we know 1/2 is equal to 2/4, right? And we have things like 0.9 repeating is equal to 1. So the idea is that numbers can take different forms but still be equal. And intuitively, we just think, well, those numbers are equal if they're sort of expressing the same quantity or the same magnitude, right? That's a little, hand wavy, but we're talking about an intuitive notion. So somewhere out there, I'm sure there's some really precise notion of what it means for two real numbers to be equal. But the main thing here is that we realize that different numbers can take, like the same number can take different forms, and we can say, oh, those two different forms are equal. Well, the same thing can happen with sets. We can have two sets that their descriptions don't look the same, but it turns out that they are in fact really the same set. And so to make ideas precise with sets, we're going to give a definition to the idea of what it means to say two sets are equal. So we'll say two sets A and B are equal means that, and of course we'll use the standard notation for equality, just means that the sets are contained in each other. A is contained in B and B is contained in A, is what it means for A to be equal to B. And if you think about it, what this really implies is that A equals B means that the two sets have precisely the same elements. Because if you have some element that's in A, it has to also be in B because of the containment. A is a subset of B. But also if you have an element that's in B, that same element has to be in A. So the two sets have the same elements. And also, if we say A does not equal to B, then we know that that means one of two things. Either A is not a subset of B, or B is not a subset of A. And what does that mean? Well, if A is not a subset of B, that means there must exist some element in A that's not in B, or there must be some element of B that's not contained in A. It could be that both of these are true, because it's not an exclusive or right here. For our or statements, one or the other or both could be true. So anyway, let's look at a few examples. S and T here, those two sets are expressed in slightly different forms. In particular, the order of the elements is, they're listed in different orders. But does that matter when we're talking about set equality? Not really. So if you think about it, all the elements of S are contained in T, right? So if you, like 1 is contained in T, 2 is contained in T, 3 is also contained in T. So all of the elements of S are also in T, and vice versa, right? This goes both ways. So S is equal to T. And the moral of the story here is that order doesn't matter in sets. And then let's look at this second example. Are A and B equal to one another? Well, it looks like on the surface, maybe not, because A looks like it has 4 elements and B looks like it has 3 elements, so how could those be equal? But in fact, if you go back to the definition of set, a set is a collection of distinct objects. In A here, we've listed the number 1 twice, but sets only care about the distinct objects that are contained within. So really, there's only one 1 there, and it's just listed twice, but that's our convention for sets. So if you think about containment, you could go, okay, this 1, is it contained in B? Yeah, there it is. Is this 1 contained in B? Yeah, there it is. Is this 2 contained in B? Yeah, there it is. And is this 3 contained in B? Yeah, there it is. So all the elements of A are in B, and vice versa. So here we have A is equal to B. And the moral of the story here is that repeated elements don't matter. So of course we would never intentionally list the same element twice like that, but it does kind of come up sometimes in sort of natural ways when you're describing sets with set builder notation, that the same element could be listed multiple ways by the membership condition. So it does happen, but we just sort of don't pay attention to redundant elements, all right? Just once an element is listed, it's just there once. All right, in this third example, the question is, are these two sets equal? What do you see as the difference between the two sets? Well, I can see that the first set, M, has a universal set of R, while the second set has a universal set of the complex numbers. Is that enough to affect the equality of the sets? Well, in fact, yes, it does matter here. It doesn't always matter, but sometimes it can really matter. So M, if we just actually list the elements of this set, which real numbers have the property that x cubed equals 1? Well, only one number in the real number satisfies this, just the number 1 itself. You can kind of think of it this way. If you were to solve that equation, x cubed equals 1, you could do that by taking the cube root of both sides of the equation. And we know from algebra class that that reduces to just x equals 1. So the only solution to the equation x cubed equals 1 is x equals 1, so that's the only element in our set. On the other hand, it turns out, and I'm going to leave you to verify that this is true, but if you are allowing complex numbers to be part of your solution to your equation x cubed equals 1, then you actually get 3 solutions. So you can check just by doing the arithmetic with the complex numbers here that if you cube all 3 of those numbers, 1, negative 1/2 plus the square root of 3 over 2 times I, where I is the imaginary unit that is just the square root of negative 1, and then negative 1/2 minus the square root of 3 over 2 times I. All 3 of these numbers have the property that when you cube them, you get back 1. So by expanding the universal set to include complex numbers, we actually end up with more elements of our set. So the moral of the story here is that the universal set matters, right? We've already mentioned this before, so this is just another example of that sort of phenomenon. In fact, we saw it previously with the example here. For that set, the set of x's where the absolute value of x is less than 3, if our universal set was the integers, well, we got this discrete set of 5 elements, -2, -1, 0, 1, and 2. But if the universal set was the real numbers, we got a whole interval here. So anyway, just driving home that point once again. Okay, so let's take a little break to do a skills check. This should be a quick one. Got 2 problems, or well, just one problem with 5 parts here. It's a true or false problem. For each of these sets, I just want you to say true or false whether the expressed relationship of equality or containment is true. If it's either way, explain your answer. So take a few minutes and do this, press pause on your video, and I'll wait for you right here. All right, welcome back. How about this first equality here? Is it true? I'm going to have to say no, because notice that the universe of this set is the natural numbers. The natural numbers are only positive. So, and this set over here has negative elements in it. So just on the basis of that, I can say no, it's false. -4 is an element of -4, -3, -2, 2, 3, 4. But -4 is not an element of the first set. That shows that the right-hand set is not a subset of the left-hand set, but the condition of equality requires that they would have to be contained in each other, right? So that shows you that the left-hand set, the right-hand set is not a subset of the left-hand set. So anyway, this fact tells you that the 2 sets are not equal because we have to have that containment in the definition of equality. Okay, in the part B, are those 2 sets equal? Yeah, they have the same elements. Just on the left-hand set, 2 is listed twice and things are not in the same order, but as we remember, repeated elements and order doesn't matter. So true, the 2 sets have the same elements just by inspection. Part C, is it true that the set containing 1, 2 is a subset of 1, 2, 3? Yes, it's true. And it's true since each element of 1, 2 is in 1, 2, 3. That's what it means to be a subset. Part D, is it true that the set containing 1 and 2 is a proper subset of 1, 2, and 3? Yes, that's true also. It's true since we already established that the set containing 1 and 2 is a subset of 1, 2, 3. And we also can see by inspection that the 2 sets are not equal. They're not equal because the set 1, 2, 3 has an element, in particular 3, that's not contained in the other set. So they don't have the same elements. Part E, is the empty set a subset of the empty set? Well, how could that be true? The empty set doesn't have any elements, so how could it have anything contained in it? But hold on a second, didn't we prove that the empty set is a subset of every set? Yes, we did. What was that fact? Fact 2.8. Okay, let's move on to the second section on sets, which is new sets from old, and also proofs involving sets. So we have several definitions we need to give right off the bat here. And you've probably seen these operations before, at least some of them, but that's okay. We'll assume you know nothing and start from the ground up. So the first operation here is called union. We have this notation A cup B. So this kind of U-shaped symbol. It's not quite a U. It doesn't have a tail, right? It's just cup like that. Anyway, that's called union. And what defines the union of 2 sets is this logic right here in the membership condition. It's the set of elements of the universe, X, having the property X is an element of A, or X is an element of B. The key logical operator here is or. And if you think about this, this has the effect of just taking the two sets A and B and just sort of combining them to form a bigger set. That's the combination of A and B. You can see why it's called union. The membership condition having the or there has that effect because if you have an element that is in A, that's good enough for it to be in the union. So any element that's in A would be in the union. Also, any element that's in B would be in the union. It could be that you have an element that's both in A and B. That would also satisfy the or condition, so that those elements would be in the union. The only way that something's not in the union is if it's neither in A nor in B. So anyway, union just has the effect of the logic of the membership condition has the effect of just lumping A and B together to form the combination of those two sets. The second definition is intersection, a cap B, so that symbol is like an upside down U kind of. And notice, so we call that intersection, and notice that the logic in the membership condition here is an and. So for an element to be in the intersection, it has to be both in A and in B at the same time. The intersection is just the elements that the two sets A and B have in common. Okay. The third definition is called the complement. A bar here is called the complement of A. These are just the elements in the universe that are not in A. So it's like everything outside of A. The fourth part here is, we read that as A minus B. So sometimes people use the notation A minus B, like a minus sign, just like you're subtracting. We also call this a set difference. But the idea is that we're going to take all the elements of A and then remove any elements that are also in B. So remove from A any elements that are also in B. You can see why it's called A minus B. We're subtracting B out of A. This is also called the complement of A relative to B, although I have to admit, I rarely hear people use that language. Most of the time people just say A minus B or the difference of A and B or something along those lines. And then lastly, we have a word to describe the relationship between A and B. So A and B are said to be disjoint if the intersection between A and B is empty. So this just means that A and B don't have any elements in common. So down here on the lower left, we have what are called Venn diagrams for each of these ideas that we're talking about above. So in this first Venn diagram here, that's the union. The shaded part is the union of A and B. So we're just taking A and B and combining them together to form one bigger set. In the second picture here, that's a sort of a graphical representation of the intersection of A and B. So we're getting the elements here that A and B have in common. And then in the third picture here, we're expressing the idea of the complement of A in pictorial form. So the complement of A is just everything that's not in A. Everything of the universe that's not in A. In these Venn diagrams, the box itself is the universe. And then, circles or bubbles inside of that box represent individual sets. In this picture highlighted here, we've got the difference A minus B. So these are the elements that are in A, but we've taken away anything that might also be in B. And then lastly, this bottom picture here shows what it looks like when A and B are disjoint. So A and B don't have any elements in common, so those bubbles are not touching each other. And then here's a toy example over here on the right, just to make sure we have our understanding of union and intersection, difference, and complement down. A union B just means take all the elements of A and B and combine them into one. A union B would be, you'd get 1 and 2, 3, 4, and 5, and 6, 7, and 8, and 9. Only thing from the universal set that we don't have in A union B is 10. B intersected with C, what do we get there? So what do B and C have in common? I see that they have in common 1, not 2, but they do have in common 3, not 4. They do have in common 5, and then that's all they have in common. C minus B just means to take C and throw away anything that's also in B. So I would have to throw away 1 because 1 is also in B. I'd have to throw away, I wouldn't throw away 2 because 2 is not in B. I would have to throw away C because C is in B. I would not throw away 4. And then I would throw away 5 because that's also in B. So when you do C minus B, you're left with only 2 and 4. And then the complement of C is just everything in the universe, and the universe is just 1 through 10. So the complement of C is just everything in 1 to 10 outside of 1 through 5. So we'd get 6, 7, 8, 9, and 10. And then when we look at the relationship between A and B there, we see that A consists of even numbers and B consists of odd numbers. So A and B don't have any elements in common, so they're disjoint. We see that A intersect B is the empty set. All right. So let's take a moment here and do a short skills check of the sort we were just doing, where you have some toy sets to play with, and you're going to calculate some unions and intersections and things of that nature. So take a few minutes, press pause on your video, and work out these, and when you come back, we'll work them out together. All right, welcome back. A union C. So this time our universe is the set of numbers the set of integers 1 through 15. So we're going to bear that in mind, especially when we're doing complements. So A union C just means take all the elements of A and C and throw them together into one pile, combine them. So we'd get 1, 2, 3. I don't need to list 3 twice. In sets, you only need to list the element once. There's no 4, we get 5. 6, we get 7. No 8, we get 9. No 10, we get an 11, and 13. So that's A and C combined together. A intersect B. What do those two sets have in common? It looks like the only element that A and B have in common is 2. Because then after that, inside of A, we only have odd numbers, and inside B, it's all even numbers. So the only element they have in common is 2. By the way, a set that only has one element, we call that a singleton. Just a little bit of terminology that I might use from time to time. Okay, the complement of A union B. So maybe we can just do this in a two-step way. Let's first find the union of A and B. So the union of A and B would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and that's it. And then we're taking the complement of that set. Let's put a bar on top of that. So this now means, what are the elements of the universe that are not in this set? Well, I've got 1, and then everything from 2 to 14 is there inside the set that we're taking the complement of. So the only thing left after that would be 15. So the complement of A union B is just the set containing 2 elements, 1 and 15. B complement, well, if B is the set of if B is the set of even integers in U, then B complement is going to be the odd integers in U. So that'll be easy enough. We can just write those down. 1, 3, 1, 3, 5, ... all the way up to 15. A minus C, so that means take the elements of A and throw out anything that's also in C. So we'd have 2, 7, 11, and 13. So these are the elements in A that are not also in C. Now for this last one, we probably want to do a multi-step process. So this would be B. Let me go ahead and write down that 2, 4, 6, all the way up to 14. So just the even numbers inside of the universe. And then we're going to union. And then what is C minus A complement? I don't know. So let me write down C is 1, 3, 5, 9. And I need to intersect, or I need to subtract A complement. Well, what is an A complement? We're going to have 1, 4, 6, 8, 9, 10, 12, 14, 15. So that'll be 2, 4, 6, all the way up to 14. Union. Okay, so then I'm going to take the set 1, 3, 5, 9 and throw away anything that I also see here amongst these elements. So I'd throw away the 1. I would not throw away the 3. I would not throw away the 5, but I would throw away the 9. So it looks like the only thing I keep is 3 and 5 here. And so looks like we're going to get 2, 3, 4, 5, 6. Then it goes 8, 10, 12, 14. All right. So next up, we need to talk about some important properties of sets. So fact 2.14 here lists several properties that are sort of fundamental properties of sets. I don't claim that this list of properties is an exhaustive list of all properties of sets, but they're some of the most basic ones. And in exercises and homework, we'll have some additional properties that are maybe less basic. Some of these, they start off as fairly obvious statements. Like it's kind of obvious, although it's something that you should prove, that A is a subset of A union B. Intuitively, this seems clear because A union B is just combining A and B, to, all the elements together, so certainly A would be contained in there. A intersect B being the elements that are common to both A and B is certainly a subset of A. So there are several sort of more or less obvious properties that we need to be aware of. Things like commutativity for union and intersection. We also have some associativity properties for intersection and union. We have some distributive properties here. Intersection distributes over union, and union distributes over intersection. Those don't seem as obvious, but they are something that we can prove, and they're useful properties to keep in mind. We have De Morgan's laws for sets here, 15 and 16, which are the set analogs of De Morgan's laws that we saw in logic. Remember, in logic, we had not P and Q is logically equivalent to not P or not Q. Same sort of property. In fact, a lot of these properties that we're looking at here for sets, we sort of inherit from corresponding properties of logic, because all of the membership conditions for sets are based on logical connectives, ands and ors and nots, negating things when you're doing complements. So that's going to be a key to proving statements like this, is understanding the logic and going back to our logic rules. So I'm certainly not going to prove all of these. I think it would be a really good exercise for you to go through and prove all of them. I will prove some of them, though, to illustrate techniques for how we prove things. So let's start by talking about how do we prove set containment. We did do one proof involving set containment, for the fact that the empty set is a subset of every set. But I really want to, this is a technique that we have to use over and over and over again, proving set containment. So when you're proving set containment, basically using the definition of set containment, we call those kinds of proofs element chasing. What we're relying on is the logic of this statement in yellow right here, that A contained in B means that for every element in the universe, if X is in A, then X is in B. In particular, the logic of this conditional statement here is really what we got to focus on. That's what we got to prove. So how do you prove a statement like that? You pick an arbitrary element in A. So you choose an arbitrary element of A, and then you argue that that very same element is in B. That's how you prove A is a subset of B. And you can see why we might call this element chasing. This is sort of an informal term to describe this process. But what you're doing is you're starting with an element, and then in A, and then you use various properties that you know and logic and whatnot, and you chase that element until you arrive that it's in B. So let's do a proof that illustrates the technique of element chasing by proving this statement about sets, which is one of the properties in the list above, the transitivity property for containment. If you know A is a subset of B and you know B is a subset of C, then it turns out that A is a subset of C, which kind of makes sense. If A is contained in B and B is in turn contained in C, it makes sense that A would be contained in C. But let's prove this fact, and let's do it carefully and rigorously. So let's start off our proof by supposing that we have three sets. So let A, B, and C be sets. Now, sometimes I'll mention or I'll give a name to the universal set. If you don't name a universal set, it's understood that there's some universal set that contains all of these sets. But if you're not going to directly use the universal set, there's no need to name it necessarily. So let A, B, and C be sets, and suppose that the hypothesis for this if-then statement is true. So if A is contained in B and B is contained in C, we're going to assume that much is true. Now, what we have to argue is that A is contained in C. Well, anytime that we want to argue that one set is contained in another, we can use that element chasing method. So to that end, we're going to let an arbitrary element X be in A. And what we want to argue, we're trying to argue that A is contained in C. So eventually what we want to arrive at is that X is in C. That will prove that any element of A is also in C, so A is a subset of C. So that's our target. We want to argue that X is in C, okay? I'll leave this here for a little bit. We'll end up erasing it to fit it into the argument in the proper place. But, it's good to have an eye on what the target is when you're trying to do a proof. So in my mind, I'm going, okay, I want to arrive at X is in C. All right, so because we know that A is a subset of B, that's one of our hypotheses, and we know X is in A, then we have that X is an element of B because of the definition of containment, right? If A is a subset of a B, that means that every element in A is also in B. So we know X is in B. And then similarly, since we know B is a subset of C, and we now know X is an element of B, we have, guess what? X is in C. That's the target that I was trying to reach. So now I know my proof is completed. So I want to point out a little bit of structure in this proof. There was a little substructure. So first of all, we were proving an if-then statement. And anytime you do an if-then statement, you suppose the hypotheses are true and you try to arrive at the conclusion. So let me use my highlighter here. So we suppose the hypothesis here and here. A is contained in B and B is contained in C. And then we arrived at the conclusion. So we see that the structure of our proof is correct in terms of we assume the hypotheses are true and then we arrived at the conclusion. But then in making the argument that A was contained in C, we used an element chasing argument which had its own set of hypothesis and conclusion. So in particular, we started to get that A is contained in C, we started with an arbitrary element X in A, and then we arrived at that element being in C. It's important to pay a little bit of attention to, when you're doing proofs, what is it that you're supposing is true? What are you trying to arrive at? And we had two levels of that going on here. What's in the blue was sort of the outer structure, and then within that we were trying to prove a containment, which I've got underlined in red, shows how that connects up. Okay, next let's look at how to do proofs of set equality. The good news is, once you know how to do proofs of set containment, you almost for free get a method for doing proofs of set equality using a method called double inclusion. Remember the definition of set equality. Two sets are equal means the same thing as we have containment both ways, right? So if we want to prove that A equals B, we just prove this stuff over here, which is two proofs. We prove two containments. A is contained in B and B is contained in A. So you can see why it's called double inclusion, right? or sometimes we call this double containment. So let's prove that here. We have two sets, A and B, and we want to prove that A minus B equals A intersect B complement. So if I want to prove this basic fact about sets, I'm going to format my proof this way. Let me start off my proof by just letting A and B be two sets. Since I'm doing complements here, I'm going to go ahead and give a name to the universal set. I'm not sure if I'll need to make reference to U, but let me go ahead and do it. I know that I often do need to make reference to a universal set when I'm doing complements. To do a proof by double containment, we will argue the two containments. So we need to show that A minus B is a subset of A intersect B's complement, and we need to argue that A intersect B complement is contained in A minus B. And the way we format this is we indicate parenthetically that we're going to do a forward containment. So this is to show the left-hand set is a subset of the right-hand set. So to prove that A minus B is a subset of A intersect B complement, we're going to take an arbitrary element X in the left-hand set. And now we're going to chase that element X until we arrive that it is in A intersected with B complement. So sometimes it's helpful to sort of think in reverse a little bit. So we want to arrive eventually at X as an element of A intersected with B complement. But what would be the previous step before that? How would I know that X is in A intersect B complement? Well, the definition of intersection requires that the element be in both of those sets. So just before that, I would need to know that X is an element of A and X is an element of B complement, right? And so I can kind of see what my target is down here. This is kind of what I'm shooting for. It's helpful to keep that in mind. So we want to be able to recognize when we're actually done with the proof, right? Or we're getting very close to the end of the proof. So let's start with what we have right now. X is in A minus B. What does that mean? Well, the definition of A minus B, so by the definition of set minus, we have X is in A and X is not in B. Okay, so now I'm eyeballing what I know now and what I'm trying to arrive at down here. Well, I've got X is in A, that's great. I need X is in B complement. But check it out. X is not in B is exactly the membership condition to be in B complement. Like the definition of B complement is the set of elements in the universe with the property that the element is not in B. So I know that I've got X is not in B, and I also know that X is in the universe. Everything's in the universe. So I can jump straight to it now. Next, since X is not in B, we have X is in B complement. Now X is in A, we already knew that, and X is an element of B complement implies X is an element of A intersected with B complement. And that's the definition of intersection, right? Check it out. We've accomplished what we wanted to accomplish because we started with our element X in A minus B, and we have arrived at that element is in the right-hand set. Thus, we know A minus B is contained in A intersect B complement. Now we need to prove the reverse containment, which I'll indicate that I'm going to do so parenthetically here in formatting the proof. So notice that I've got the subset symbol reversed to indicate that I'm doing the reverse containment of what I was doing originally. So let's do that next. So if we want to prove the reverse containment, so to prove A intersect B complement is a subset of A minus B, we're going to start by letting X be an element of A intersect B complement. Now, basically what we're going to do is run that previous containment proof in reverse. You can't always reverse the logic, but this time we can because the only thing we used in the previous argument was definitions, and definitions are all reversible. They're if and only if statements. So since X is in A intersect B complement, we have X is in A and X is in B complement. And that's just using the definition of intersection. Since X is in B complement, we have X is not in B. So that's the definition of complement. Now we have x is in A, and we know x is not in B. So that's what it means to say x is in A minus B. And you see the logic of it is that we started with x in A intersect B complement, and we arrived at x is in A minus B. So that shows the containment that we want. And now, having proven both of these containments, we've proven equality, right? So we're done. So this proof right here is really worth studying and making sure you understand it through and through. It's a good method. When we're proving set equality, I would say probably 90% of the time, this is the method that you're going to want to use. There is sometimes a quicker way to prove set equality just by arguing that the membership conditions are logically equivalent for the two sets, which is a way we could have proved this one. And when you can prove it this other way that I'm going to talk about soon, it's usually a shorter, more concise proof. But this is the method, double containment, that is more widely applicable. So it's really the method that you're going to want to master more than anything. So I'll come back to this other method in a little bit, but for now, let me just reiterate, the method of double inclusion really most of the time is the way to go. So study this proof and make sure that you can do a proof like it. Okay, another thing to talk about when we're proving facts about sets is that logic is your friend. All of the sets definitions involve logic, ands and ors and nots. And so manipulating the logic helps you understand, how to see relationships among sets. Let me give you an example of what I'm talking about here. Let's consider the logic of the sentence, X is an element of A intersect B complement. Okay? When you say X is an element of A intersect B complement, what does it mean to be in the complement of a set? It means that the element is not in the set. So this is the same as X is not in A intersect B. But when you think about the logic of that, that's the same as not X is in A intersect B. But now let's think about what's inside the parentheses here. What does it mean to say X is in A intersect B? Well, that means X is in both A and B. So this is not X is in A and X is in B. And now remember De Morgan's law. De Morgan's law says that to negate an and statement, it becomes an or, and then you negate the individual pieces. So this becomes not X is an element of A, or in other words, X is not an element of A, and then or, and became or, and then X is not in B. Let's continue the logic here a little bit. Another way to characterize when you say X is not in A, to make that a positive statement is to say X is in A's complement. Similarly with B, X not in B, we can say that's the same as X is in B complement. And lastly, check it out. If X is in A or X is in B, this is exactly the membership condition to say X is in the union of those two sets. So we could say X is in A bar union B bar. So this is just playing around the logic, right? But check it out. The statement that an element X is in A intersect B's complement is logically equivalent to saying X is in A bar union B bar. So that basically tells you that those two sets are equal. And that's exactly what we're going to prove next. Now I'm going to take advantage of that logic that we did there. That logic is almost a proof. I'll show you how to use that logic exactly to make a really short proof. But for now, to prove that A intersect B complement is equal to A complement union B complement, I want to do a double containment argument again. So let's do that. So I'm just going to jump straight to the two containments. So to prove the forward containment, I would start by saying, well, let X be an element of A intersect B bar. And then I'm just going to use the logic that I had up here at the top. Then by definition of complement, we know X is not A intersect B. That is, not X is an element of A intersect B is true. Thus, not X is an element of A and X is an element of B is true. And by De Morgan, X is not in A or X is not in B. That is, X is an element of A bar or X is an element of B bar. So by definition of union, X is an element of A bar union B bar. And notice that at this point we have proven that if we start with X in the left-hand set, we've argued that that very same X is in the right-hand set. And so that proves that containment. And then the reverse containment basically just amounts to reversing all that logic. I'm just going to leave this for you to do, but basically you can just reverse the logic. So anytime that you see you got one of these arguments where all the logic can be reversed, it's telling you that it's probably possible that you can make a shorter, more elegant argument. And that's the topic I want to talk about next. So proving set equality via equivalence of membership conditions. So let me show you how that would look for this same thing that we just proved. So what I could do here is just write down the definition of the set. So A intersect B complement is, by the very definition, the set of elements in the universe having the property that X is not in A intersect B. So this is by definition of complement. And then that in turn I can write as the set of elements in the universe having the property that I'm just going to emphasize, this is not X is X is in A intersect B, like so. So this is just more of a notational issue of what not an element means. Not an element is just negation, right, of is an element of. And then now I'm going to apply the definition of intersection. Say this is not X is in A and X is in B. So here we're using the definition of intersection to say X being in A intersect B means X is in A and X is in B. The next step would be to use De Morgan's law of logic. So this becomes X is not in A or X is not in B. De Morgan of logic. And then we can write that as this is X is in A's complement or X is in B's complement. So this is definition of complement. And then lastly, we can use the definition of union. Well, we can jump straight to it. We can just say this is exactly A bar union B bar. And that's just definition of union. So here we've proven that the two sets are equal just by establishing, a sequence of set equalities. And certainly equality has a transitivity property. So, we've shown that the left-hand set equals the right-hand set here through a sequence of equals. And so I didn't have to do a double containment argument here because each one of these steps involved just a definitional thing. So I got equality all the way through this. Everything was reversible. So anytime you're doing a double containment argument and you notice that every step in one of the containments was completely reversible, then probably you could have done a proof like this a little more concisely. But like I said, this kind of proof is sort of niche. Every once in a while you get to use it and it's kind of cool when you do, but more than 90% of the time you're probably going to find yourself needing to do a double containment argument. So that's going to be the method that you really want to focus on. And we can prove this fact with double containment too. Just this makes it a little shorter and a little more concise, But we did the double containment argument here. So anyway, use it if you can, but if it's not there, don't try to force it. All right, so this would be a good time to do a skills check. I've got a couple of proofs I want you to do, so this will be a skills check that may take you a little bit longer just because proofs tend to take longer to do. The first one is a proof involving set containment, and you're proving a conditional statement also. If A is contained in C and also B is contained in that same set C, then the intersection of A and B is contained in C. So I want to prove that one. So this one's more of a set containment proof that you have to deal with. And then the second one is a set equality proof. And you can do that one either by double containment, or you could do it by the just working with the membership conditions, it turns out. So give those two a whirl, and we'll see what you come up with, and then we'll work through them together when we come back. Okay, welcome back. Let's run through these two proofs. So for the first one, let's start off by letting A, B, and C be sets. And let's suppose the hypotheses of the conditional statement are true. So we need to suppose A is a subset of C and B is a subset of C. Now, what we got to prove is the then part. So to prove that, we're going to take an arbitrary element of the smaller set. So let's let X be an arbitrary element of A intersect B. And of course, what we want to argue is that that element is also in C. So that's our goal. We'll know we're done when we have argued that X is definitely in C. So I'll leave our target there just so we can keep an eye on it for a moment. Now, because X is in the intersection of A and B, we have, by the definition of intersection, X is in A and X is in B. Since X is in A, and we happen to know by hypothesis that A is contained in C, recall, then we obtain X has to be in C, right? Well, it looks like we're done, which is kind of odd because, you know, we never made use of the fact that X was in B. But it doesn't matter. Just knowing that X was in A, we could have used X was in B. That would have also done the same thing. We would have said, well, B is contained in C, so X has to be in C. So either way, we end up with X is in C, but we didn't even have to really work with the fact that X is in B. That's always a little concerning when you don't use some hypothesis or some immediate consequence of the hypotheses, but in this case, it just worked out really simple. So we now know that X is in C. So look, we started with our X in A intersect B, and we arrived at X is in C. And so as soon as that happens, you know you're done. Putting down my little square and calling it done. All right, for the next problem, we have three sets A, B, and C, and we want to prove this equality of sets. I'm going to do this by arguing that the membership conditions are logically equivalent. So I'm going to do it this way. I'm going to say A union B intersects C is the set of elements of the universe having the property. Now, since this is, we're talking about, we're going to apply the definition of union here. So to be in the union, you have to be in one set or the other. So this would be X is in A or X is in B intersects C. Here we apply definition of union. And then this in turn is equal to the set of X's in U. I'm going to apply the definition of intersection to break out the logic of what it means to say X is in B intersects C. So this would be X is in A or, and just for emphasis, I'm going to put a parenthesis here, X is in B and X is in C. So here we apply the definition of intersection. Okay, so now here's where logic will be our friend. We had a tautology back when we were doing logic that was something like this. P or Q and R is logically equivalent to, we had that or is distributed over and, so it became like P or Q and P or R, like that. So that was a tautology. And so I can apply that to the logic that I'm seeing right here because it's of that form, right? What you see underlined above is the left-hand, sort of the form of that logic. And then I'm going to convert it to that using this tautology. Okay, so this becomes X is an element of A or X is an element of B and X is an element of A or X is an element of C. And I'm just going to put tautology here, but you know which tautology I was referring to. Maybe if I wasn't being lazy right now, I would look up the specific part of that one long list of tautologies and give it a reference there. But you know the one that I'm talking about. And then this becomes the set of X's in U. The stuff in the first set of parentheses here, X is in A or X is in B, that's what it means to say X is in A union B. Then we have an and then that second set of parentheses there is what it means to say X is in A union C. So we just use the definition of union here. And then lastly, we have X is in this set and X is in this set. That's the definition of intersection whenever you say the same element is in two separate sets. So this is just by definition A union B intersected with A union C. Definition of intersection. And that's the proof, because we've showed that the left-hand set equals the right-hand set through a sequence of equalities. So yeah, remembering the logic can be really helpful. Now, could we have done this using a double containment argument? Yes, we could. What we would see is that once you do one containment, you would see that, oh, all those steps were reversible, and so then doing the reverse containment would just amount to just reversing all the steps of the previous proof, and it would just feel like you're doing double the work. But that would be okay, and it would be good practice for you to do this, take this proof that we've done here and convert it into a double containment proof. It's good practice for just doing double containment, because like I've said, double containment is going to be your go-to method, really, especially as we start working problems like proving properties of functions and relations. Almost always there we have to do double containment arguments. Okay, next topic is the topic of power sets. So A is just any old set. The power set of A, denoted by this script P of A, is the set of all subsets inside of A. So the power set is just the set of all subsets of a set. So let's play around with that with this toy example here. So starting with A is the empty set, what would be the power set of the empty set? So what sets are subsets of the empty set? Well, there's only one set that is a subset of the empty set, and that would be the empty set itself. So the power set of the empty set is the set that contains the empty set. Notice this is not the same thing as just the empty set. This is a set that contains something. So this set that we're talking about here has one element. That one element is the empty set. So don't think, just, a little word of warning, this is not equal to the empty set. Okay, so I just want to point out this set has one element. Okay, how about the next one? If a set just contains the element 1, then what's its power set? Well, one thing we know, one set that's a subset of every set is the empty set. So anytime we're looking at the power set, we always get the empty set in there. And then the only other set that is contained in a one element set is that set itself. So this. And notice that here we have two elements. The two elements of the power set are the empty set and the set containing 1. Okay, we go to a set that contains 2 elements. We know the empty set is a subset. We can do each of those singletons, like the set containing just 1 and the set containing just 2. Those would be subsets of the set containing 1 and 2. But also we get the whole set itself as a subset. Every set is a subset of itself. So here we get 4 elements. Let's do one more. The power set of a 3-element set with 1, 2, and 3 in it, you'd get, well, the empty set's always there. You get all those singletons, 1, 2, and 3. Then you would get the subsets that contain 2 elements. So you can do a few of those, like you get 1 and 2, 1 and 3, 2 and 3. And then you get the whole set itself, 1, 2, and 3. And then that's it. And notice here, how many elements do we have? 1, 2, 3, 4, 5, 6, 7, 8 elements. So I ask you down here at the bottom, do you notice a pattern in terms of how many elements are in the power set of an n element set? So the pattern is it's powers of 2, right? Let's see. Be 2 to the, an element. So if you have 0 elements, you get 2 to the 0, that's 1. If you have 1 element, you get 2 to the 1. Yeah, so 2 to the n elements in its power set. I state this without proof. I think to prove it, we would need a process called mathematical induction, which we're not going to learn for a while, but we will learn it. So this is something we could prove by the end of the course, but not right at this moment. In any event, you can see why it's called a power set now, because it's making reference to the number of elements as a power of 2. In fact, sometimes I've seen this notation, the power set of A, sometimes people write it this way, 2 to the A, as a reference to the fact that you get that many elements in the set. People even use that notation when it's an infinite set. But when you're talking about a finite set, If you got a finite set with n elements, the power set of that set will have 2 to the nth elements, where n is the number of elements. So here's a topic that I want to finish up this section on. I want to talk about how you can use Venn diagrams to test conjectures about sets. So Venn diagrams, one thing we have to really understand about Venn diagrams is that you don't prove anything with a Venn diagram. A Venn diagram is just a visual aid to help you sort of understand and comprehend the relationship between sets. But it in no way constitutes a proof. Can it help guide your proof and guide your intuition? Absolutely. But don't confuse Venn diagrams, which are just pictures, with proofs. I've got this problem here, and I'd like to sort of I've got this relationship among sets down here that I don't know if it's true or not. Just looking at it, I have no idea. And it involves this definition here. This set operation with the triangle in the middle is called a symmetric difference. So one thing we should probably try to do before we try to do anything is just understand what this symmetric difference is, maybe through a Venn diagram. So let's do a Venn diagram for A symmetric difference B, a little triangle thing. All right, well, let's see. I'm going to draw a little box here for the universe. And I'm going to need 2 bubbles for the 2 sets. So here's A, here's B. Now, I want to try to shade the part that is the symmetric difference. First of all, I know what A minus B looks like from when we first talked about Venn diagrams for the basic operations. I don't know, let me shade that with the blue highlighter here. So that is A minus B, and also over here would be B minus A. So on the left-hand side here, I had A minus B, and then over here, I had B minus A. And so if I'm looking at this definition at the top, the union is just those 2 shaded regions thrown together, combined, right? So what I have shaded here is the Venn diagram for the symmetric difference. Okay, so now maybe we can make a Venn diagram. So if I want to sort of test whether this relationship is true, what I can do is make a Venn diagram for each side of the equation. And if those Venn diagrams match, that tells me that those 2 sets are probably actually equal, and then I can prove it using methods of proof that I know. And if the 2 Venn diagrams that I get are not looking the same, it tells me that the 2 sets are probably not equal, and then I try to come up with a counterexample to show that they're not equal, like in general. So let's make a Venn diagram. Okay, so here's sort of a generic way that we can have 3 sets sort of mutually intersecting one another. And what I want to do in this picture is to shade the region corresponding to the left-hand side of this equation. So for this this is going to be the Venn diagram of the left-hand side of this equation. So this is going to be A union B triangle C. And then I'm going to do the right-hand side of that equation. So let me make a copy of my Venn diagram here. And then this will be the Venn diagram for A union B triangle A union C. Okay, so basically I just want to do the shading. So for the first one, I'm going to first do the shading for B triangle C. So for B triangle C, so according to the picture on the left, if I just apply that to B and C, I would get, these 2 loon-shaped regions like here and here. All right, so there's this much of it. That's B, the symmetric difference of B and C. And then I just want to union that with A. So let's go ahead and add A to what we already have. So if we add A to what we already have, I'll just continue shading here. So everything's shaded. So I'll go ahead and shade this part in here and all this part out here too. We got to throw that in. So our Venn diagram for this set, basically the only thing that didn't get shaded was this little region right here in between B and C. Now let's see if we get the same thing in the bottom Venn diagram. So first thing I'm going to do is I'm going to shade A union B. I think this time I'll use some lines. So A union B, I'm just going to shade the combination of A and B here. Sometimes these Venn diagrams can get a bit cluttered as you're shading things. Like it'd be hard to see what you've actually shaded, but I'll try to use colors and keep it pretty clean. So that's A union B in yellow there. Let me underline that in yellow to sort of give a color code. And then I'll do similarly A union C. I'll do that in green. So A union C looks like this. Okay, so now what I've got to do is do the symmetric difference of what's in yellow and what's in green. So to get the symmetric difference between the yellow and the green, so first I take what's in yellow and throw away what's in green. So if I took what's in yellow and threw away what's in green, I would get this. And then at the same time, I want to take what's in green and throw out anything that's in yellow. And that would give me this stuff down here. So the symmetric difference that I'm going to get between these two sets that are currently shaded yellow and green is going to be the stuff that I had in red there. By the way, this was the green. So my symmetric difference, I'm going to shade that with a highlighter. It'll be the stuff I'm getting ready to shade in blue. It'll be this stuff combined with this stuff. Okay, so now when I compare these two pictures, the stuff that's shaded in blue certainly doesn't look the same. So my conjecture here is that they are not equal. So how would you go about proving that? You would have to come up with three specific sets to serve as a counterexample of that equality. So this is a general statement that says, basically for any sets, A, B, and C, that equation holds. So if I want to disprove that universally quantified statement, I need to come up with a counterexample. The Venn diagram can help guide me. So like, why are these things different? I don't know. It looks like just about we could come up with a counterexample using just about any three sets that sort of mutually overlap, as long as they, are not equal sets somehow. So maybe I'll just do something like, let me just try something here. Maybe if I say, for a counterexample, okay, so for maybe a counterexample, I'll do like A equals the set containing 1, 2, and 3. And I want B to overlap with that. Maybe I'll do 2, 3, 4. And I want C to have some overlap with those other two sets. So maybe it'll be 3, 4, 5. And so we can then look at what is on the left-hand set, A union B triangle C. So A union B triangle C would be A union B minus C union C minus B. So that would be A union, okay, what's B minus C? So take B and throw out the things that are in C and you're left with 2. And then if you do C minus B, you'd only be left with 5. If you union those three sets, A union with singleton 2, union with singleton 5, you would end up with 1, 2, 3, 5. And then we can see the other side of that equation, which was A union B triangle A union C. A union B triangle A union C. So A union B is 1, 2, 3, 4. Then we want to triangle that with A union C would be 1, 2, 3, 4, 5. So then you take the first one, subtract out the second one. So 1, 2, 3, 4, take away 1, 2, 3, 4, 5, you get the empty set. Then union. Then you take the second set and throw away the first set, and you would just be left with 5. So this set just comes out to 5. So, and we see that these two sets are not equal, right? So there's a counterexample. Okay. I think that'll be a good place to stop, and I won't do a skills check on doing Venn diagrams, but we will likely see something like that in the homework exercises. So take a good look at this one. And like I said, you could find, the Venn diagram could have ended up being the same for both sides of the equation, in which case that would have been evidence that they're equal, and then I would have tried to construct a proof at that point. So Venn diagrams can be fun to play with, and if you like to color, they're a whole lot of fun. But mainly they're just sort of to give us a little evidence to tell us which way to go. Try to prove it or try to disprove it. All right, so let's stop there and maybe take a second to reflect on what are some of the big topics that we covered today. So we introduced sets, set notation. In particular, set builder notation is going to be really important because it's sort of the most flexible way to describe sets, and it always works. And then we talked about set containment and set equality, what that means. So we have precise definitions for what we mean by set containment and set equality. And based on those definitions, we came up with a couple of methods for proving set containment and set equality. So to prove set containment, we have this method of element chasing, where you take one element in the smaller set and argue that it's in the bigger set. And then we had proofs for doing set equality. I gave you a couple of ways of doing that. The main way is just basically straight use the definition of equality and do a double containment proof. So if you want to prove that one set A equals another set B, you argue that A is contained in B, and conversely, B is contained in A. We can also sometimes argue two sets are equal by arguing that the logic defining the membership conditions for the two sets are logically equivalent. So, but that way doesn't tend to be as applicable to most situations. So I would mainly focus on doing double containment arguments. And then lastly, we looked at power sets, and then we looked at how to use Venn diagrams to sort of guide your intuition and to point you in the right direction on whether you want to prove some sort of claimed relationship between sets or disprove it. All right, so let's stop there, and we'll talk again soon. Goodbye.